In this video, we're going to review waves, wave motion, wave behaviors, sound, and light, and wave interference. First thing to remember about a wave is that waves carry energy through a medium. You've got to have some sort of medium to carry a wave. Remember that a transverse wave is a wave where the disturbance is perpendicular to the direction the wave is traveling. So something like that, and light is a good example. A longitudinal wave is a wave whose disturbance is parallel to the direction the wave is traveling. A good example of that is sound. To actually draw something like that, you would have to draw the medium itself. So if you remember your lab where you were using the snakies out in the hallway, you pinched together some coils and let go of them. That created compressions and rarefactions, and you had a longitudinal wave. The parts of a wave that we need to remember: the height from equilibrium is the amplitude, and the distance between two crests or two troughs or any 2 points on the wave that repeat is the wavelength. The amplitude depends on the energy used to create the wave. So in your lab you change the amplitude by shaking the spring harder. The wavelength depends on the velocity of the waves and the frequency. The bigger the frequency, the smaller the wavelength. Remember, frequency simply means the number of waves per second, and we measure that in a unit called hertz, which is just waves per second. The velocity of a wave depends only on the medium that it travels through. So, for example, the speed of sound in air is a constant. It doesn't depend on how how loud or how quiet or how high-pitched the wave is. A sound wave in air will always travel at the same speed. Remember the relationship V equals F lambda. Lambda is the wavelength, V is the velocity, and F represents the frequency. You may have a problem or two using that equation. Remember that when you increase the frequency of a wave, the wavelength will decrease. So the more waves you create per second, the closer together they're going to be. You will be asked questions about how you can change all those things, like from your lab. Behaviors that a wave exhibit. First part we talked about with boundary effects, like what happens when a wave goes from one medium to another. There's 3 things that could happen. The first is reflection. The wave could simply be sent back away from the new medium. Good examples are mirrors and echoes. So when light strikes a mirror, the angle of incidence and the angle of reflection measured from a normal line are the same. That's an important fact to remember. Also remember that we always measure angles from the normal, perpendicular line. The second thing that could happen is transmission. That just means a wave moves into the new medium, kind of like light going through a piece of glass. If you draw the wave, remember, but because the medium controls the velocity, it's going to look different in one medium than it does the next. So in this example, I've drawn a light wave in air and then a light wave in water. Light slows down in water. So since the velocity changes, but the frequency does not, then the wavelength is going to change. So when light goes into water, the waves are going to be closer together. The third possibility is absorption. Wave just loses its energy to heat. So if you try to look into a car window on a sunny day, some of the light's reflected. You can kind of see yourself in the window. Some goes through. You can kind of see into the car. And then some would also be absorbed, like the window gets hot because it's been sitting in the sunlight. More wave behaviors. Remember that refraction is what happens when you transmit a wave at an angle. And again, remember those angles are always relative to the normal. So if light tries to go from air to glass, it's going to be bent. The angle of incident and the angle of refraction are different. The thing that you need to remember is that the angle is larger for the faster medium. If a medium's faster, that means it has a lower index of refraction. So remember the lab where you guys measured the angles and then you calculated the index of refraction. You won't be asked to calculate the index of refraction, but you will be asked to identify which medium is which, or identify the path that is possible for light to travel when it goes from one medium to the next. The second wave behavior, the other way to bend a wave, is called diffraction. It's the bending of a wave as it goes through the opening in a barrier. So here are some water waves going to the opening in a barrier. As they go through, they're going to be bent into kind of like a circular pattern. A good example of this is sound diffracting through an open door. When somebody is talking in the hallway and the door is open, you can hear them even though you can't see them because the sound will diffract through that open doorway. Another effect that we talked about is the Doppler Effect. That's the apparent shift in frequency when the wave source is moving. Keyword is moving. If it moves towards you, then the wave frequency is higher. If it moves away from you, then the wave frequency is lower. So a good example is an ambulance siren. Draw an ambulance. The waves in front are closer together because the ambulance is moving towards them. The waves in back are farther apart because the ambulance is moving away. So in this example, the ambulance is moving to the right. So somebody standing to the right would hear a higher pitch. Somebody standing to the left would hear a lower pitch. Another behavior that's specific to wave is wave interference. This occurs when two waves are superimposed, meaning they are in the same place at the same time, in which case they create a new wave, and the amplitude of that new wave is the sum of the original two amplitudes. So we do pictures like these, where two waves are going to interfere with each other. When they interfere, we just add up their amplitudes, but the original waves aren't changed. So after they are superimposed and they interfere, they keep moving as if nothing ever happened. When waves are lined up crest to crest, they are said to be in phase, and that leads to constructive interference. You have a bigger wave than what you started with. Remember, nothing is actually being constructed. There's nothing new created. It's just that at that spot, the amplitudes add up. If the two waves interfere like this, where it's a crest and a trough, we're going to get a smaller wave. Again, the two waves don't affect each other. If they're crest to trough like that, then they are said to be out of phase, and that gives us destructive interference. Again, nothing is actually being destroyed. You're simply getting a smaller wave at the spot where they interfere with each other. One example of wave interference we saw in class is a standing wave. That's the pattern created by two identical waves traveling in opposite directions. I showed you this in class with the string vibrator. And we used the strobe light to freeze the wave in time so we could actually see the pattern created. So if we draw a standing wave, at time t equals 0, it'll be constructive interference. It'll look like the blue wave. At time t equals 1/4 of a second, then the two waves will have shifted by 1/4 of a wavelength in both directions, and we get destructive interference. 1/4 of a second later, we're back to constructive interference. And then 1/4 of a second after that, we're back to destructive interference. And so we get this oscillating pattern between the red line, the green line, the blue line, the green line, the red line, and the yellow line, and then the pattern repeats itself. The place where there is never any movement is referred to as a node, and the point where there's maximum movement is referred to as an antinode. You may be asked to count standing wave antinodes and nodes or draw them. So for example, the standing wave I've drawn has 7 nodes and 6 antinodes. We studied sound in detail. Remember, sound is a longitudinal wave created by some vibrating object, typically in air. So when you talk, it's your larynx that vibrates. When you ring a tuning fork, it's a tuning fork that vibrates. When you play a guitar, it's a string that vibrates. Remember that pitch is your perception of frequency. Higher frequency, higher pitch. Loudness or volume is your perception of amplitude. Louder sound waves have a higher amplitude. We did a lab with resonance. That's where waves of an object that are at an object's natural frequency cause it to resonate or cause it to vibrate. So another way to say that is it increases the amplitude of vibration. So we did that lab where you were using a tuning fork above a piece of pipe and water, and when you got the pipe at the correct length, that matched the natural frequency of the air inside, and you heard the tuning fork get louder. That's an example of resonance. Another example of resonance is when you took one tuning fork and made it ring and you held it next to another identical tuning fork, and then the second tuning fork rang. The reason the second tuning fork rang is because the waves from the first one were at the natural frequency of the second one. We studied light and electromagnetic waves in detail. There's 4 things I need you to remember about light and electromagnetic waves. The first thing is that they only differ in frequency. The only difference between red light and blue light is the frequency. The only difference between light and radio waves is the frequency. They always move at the speed of sound, speed of light, and the speed of light is 3 times 10 to the 8th meters per second, and we symbolize that with the lowercase c. They can move through empty space. That's how light from the sun can reach us. And then the 4th thing to remember is that the energy depends on the frequency of the light or the electromagnetic wave. So low frequency waves have low energy, high frequency waves have high energy. So in order from low frequency to high frequency, we need to remember the order of the electromagnetic waves, going from radio, microwaves, infrared, visible light, ultraviolet, X-rays, and then gamma rays. Remember that the energy depends on the frequency, so those are also listed in order from lowest energy to highest energy. If we break down the visible light, remember that the colors of light correspond to the different frequencies, and they go in order of the rainbow. Remember the acronym Roy G. Biv that you learned in grade school. Disclaimer, remember your physics teacher is colorblind, and so those colors may not exactly match up, but I did do my best. Remember red, orange, yellow, green, blue, indigo, and then violet. Red is the lowest frequency, violet is the highest frequency of light. We took 3 flashlights that were colored and we mixed them together to see what colors you create when you mix different colors of light. Remember that black is the absence of color. Black means that it's absorbing all the light. We had a red flashlight, a blue flashlight, and a green flashlight. Remember when we mixed the red and the green, we got yellow. When we mixed the red and the blue, we got magenta. And when we mixed the green and the blue, we got a color called cyan. And again, those colors may not match up exactly. When you mix all 3 of those, you get white light. Also remember from that demonstration that if you shine light onto something that doesn't have that color in it, then it's going to appear black. So if you shine blue light on a red piece of cloth, the red piece of cloth will appear black. That's the end of this review video. If you have any questions, please see me during tutorial times, and we'll get them cleared up. Please do be sure to answer all the questions in your review so that you're ready for your test.